I will begin. Heavenly Father, we thank you for this day. And Lord, I thank you for these students. Just pray that you be with us today. Help us just to glorify you what we do, Lord. In your name I pray. Amen. So one of you asked me a question about the homework, which I will address briefly. And so the question is how to find the center of mass, for a curve. So if this is a curve which, has parameterization R of t, for t, say t0 less than or equal to t, less than or equal to t1. Suppose you want to find the center of mass for that. You're given that the mass per unit length, lambda, is dm ds. Right? So to calculate the total mass, you just integrate dm over the curve, which, by the way, you'd actually do that by integrating lambda ds. Now, the problem that you're given in the homework, lambda is a constant, so this is not particularly exciting. Really, that's just a way of asking you to calculate the arc length times lambda. All right. Then, the center of mass at x bar, y bar, z bar, well, you calculate the average x by the weighted average, so to speak, 1 over m, integral over the curve of x dm, which, by the way, is really 1 over m, the integral of x lambda ds over the curve, and likewise for y bar and z bar. So that's what you got to calculate for that problem. You got to calculate these integrals to figure out what the center of mass is for as that happens. I think it's 2 winds of the helix, but it's not exactly it's not a circular helix. It's like some sort of exponential helix. But if you calculate that carefully, you'll find out that the arc length, you'll find out that ds is actually not that bad. I mean, what is ds? How do you actually calculate ds, by the way? Remember from the first part of the course? I think this was even before test 1. We defined the integral of, I think we just had, I don't know if we, well, anyway, this is what it is. I'm not sure if we did it or not, but what this means is integral from t0 to t1. You take the function, you evaluate it at r of t, and then you multiply that by the length of dr dt. You might recognize this. This is ds dt. It's the speed. So to calculate the integral, so the f, quote unquote, here is either just lambda, or x times lambda, or z times lambda, or y times lambda, depending on which integral of these 4 you're doing. So that's that problem. Which problem am I talking about? 96? All right. Any other questions about homework? That's not a question. I asked for questions. What's your question? Still not hearing a question. Somebody have their problem sheet. I'll look at it and see if I can understand what you're saying. 98. Nathaniel has offered his up. Thank you. All right. Well, we define flux. This is a vector field. And I suggest you use the divergence form of Green's theorem. So, yeah. So I guess that here, let me write 2 things for you. We had, what are the 2 forms of Green's theorem that we had? So the spelling varies for me depending on the day, but anyway, the one we had was that the integral of p dx plus q dy was the double integral of partial q, partial x minus partial p, partial y, right? And so this would be over the region, the boundary of the region rather, and this is over the region. And this still makes sense with the understanding that the region could have holes in it, right? So like, if your region had holes like this, the outer edge is clockwise oriented, but the inner edge is understood to be counterclockwise oriented, right? So like here, the boundary of R is C out union C in 1 union C in 2. These are both clockwise oriented. This one's counterclockwise oriented. That's what the natural orientation of the boundary of R is, right? So this is the full form of Green's theorem. As it relates to what? Now this, of course, is the integral of f dot dr, right? Over the boundary of R. And on the other side, we have the integral over the curl of the vector field p, comma q, comma 0. And it's actually the z component of that, if you want me to get technical. Not that you do, but I'm going to. So there you go. So this is actually having to do with the curl of the PQ0 vector field. I mean, this is, so sometimes I call this the curl form of the divergence theorem. The other form of the divergence theorem, right? And what is this, by the way? This is the work, or you could call it the circulation of PQ along the boundary of R. Okay? That's most simple, of course, when there's no hole and it's just a simply connected region and the boundary is just the outer edge. Okay? But nevertheless, we have this theorem. Now the divergence form says that the flux through the curve, which we worked out is the integral over the boundary of the region of, what was it? You guys are going to have to help me out here. What do we got? P dy? What's that? So P dy minus Q dx, right? So this calculates the flux of the vector field P comma Q through the curve C. And we worked out that that's in fact equal to the integral of what? Partial P, partial X plus partial Q, partial Y, dA. This is also known as the divergence of the vector field P comma Q comma 0. So this is the so-called divergence form of Green's theorem. So we can either use use Green's theorem to calculate the work done by a force field around a loop, right? Or we can use the Green's theorem as a sneaky way to calculate the flux of a vector field through a curve. So in the problem you guys just asked me about 98, I'm suggesting that it's probably easier to take the divergence of that vector field and then calculate the area integral as opposed to calculating this directly. I mean, I don't know, but that's, so I think you're supposed to use the second thing, the last thing I wrote here to do that problem. Okay? So first order of business is to calculate partial P partial X plus partial Q partial Y. We're talking about 98? All right, so the divergence is really quite nice here. It's just 3x squared plus 3y squared. And you're supposed to calculate the integral of 3x squared plus 3y squared in the unit disk. This is like 3 lines. You just use polar coordinates, yeah, to calculate the area integral. So I would, yeah, I mean, if I'm going to, yeah, certainly, if I'm going to do the integral of 3 times x squared plus y squared dA over, x squared plus y squared less than or equal to 1, that screams at me, use polar coordinates, yes. Any other questions?
On 92, it was like prove two equations. Give me like hints about like how to do it.
Well, you got two choices. You can either write it out in components and just work through it, or you could try to use the epsilon notation for the latter one. But yeah, it's just pretty much just write down the definition of what that is and use the product rule on components. That's pretty much it. Yeah. Other questions? Yep.
For 94, that also screams convert to sphericals, but we don't have spherical definitions of the curl and divergence, do we?
For 94, yeah, well, fair enough. If you did know the spherical formula for the curl and divergence, that would make it easier. But you can do this in Cartesians. It's not too bad. I mean, if you want to use this, if you want to look in my notes and find the curl and spherical coordinates, you're welcome to do that. It's not, it would take me a little bit of time to really derive those in here at the moment. I might get around to that eventually. But the curl and sphericals, it's not as simple as you might think. It's not just, well, we've already seen that the gradient in spherical coordinates is kind of weird, right? Well, it gets weirder when you look at the divergence, and let me see if I can tell you. That is a reasonable question, if I can find it. I don't remember where I put that in the notes. It may not actually be in my current type notes. It may only be in my handwritten notes. We're talking about the identity problem again? Which one are we talking about? The curl one or the divergence one? What? Both of them. Okay. Yeah. If you don't mind emailing me your question about the problem you just asked me about, Nathaniel, I'll send you guys a little note about where to look it up. I have formulas for the curl and divergence in spherical and cylindrical coordinates in my handwritten notes, which predate these, and I know where those are, so I'll send you a link, but I don't have it right off the top of my head. And I think you're right. I don't think I haven't typed them up yet. Yeah. So the question you're asking me about is, I'll focus on this one, the divergence of F times G, right? So what is this? This is, well, may I suggest that we look at it this way? It's the sum I equals 1 to 3 of partial xi of f times, well, g sub I, because fg is equal to what? It's equal to fg1, fg2, fg3, right? So this is the ith component of fg, right? What is the formula for the divergence? It's the ith derivative of the first ith component plus summed from I equals 1 to 3. I mean, it's x with x, y with y, z with z, or x1 with x, x1 with the first component, x2. So I'm using the notation, guys. x1 is x, x2 is y, x3 is z, which is, a helpful notation for this kind of question. And then, well, that is what? Partial f partial xi gi plus f partial gi partial xi. Right? How do I know that? Yeah, that's the product rule. And then it's just a question of interpretation. See this, what is this? Well, this first piece gives me the gradient of f dotted with G. And this piece, well, that's just F times, that's exactly, well, we can pull the F, I'm out right, fine, right one more step. Sum I equals 1 to 3 partial GI partial XI. Well, this is nothing more than the divergence of G. Oops, I think I did half the problem for you. Sorry about that. So the gradient of F dotted with G, you'll recover. Okay, yeah. So there you go. I mean, that's. So what you said you're missing half the terms. What did you mean by that?
From the example I got from both, it didn't show
It had a C in there and it called that a constant. So when we were looking at it, we were just like, oh, F is the same as C.
No.
F is a function.
So there's the difference, is that F is not a constant, F is a function, so I have to do the product rule.
Then that makes way more sense.
Now, to start the other one, you just need to, calculate smart. So what is it? The curl of F times G again? Is that right? So I won't do the whole thing, but I'll start you out. So this is, by definition, the sum ijk of, let's see here, epsilon ijk partial I of, well, F times Gj, and then x hat k. There's my formula for the curl as it applies here, because the ith component of the thing being curled is F times Gi. And you go from there. It's a product rule. Rewrite it as two sums. If I write much more, I've solved it. Or, if you like, you can write it out in gory, component notation, and there's 3 product rules and 6 total terms, and then you can rearrange it to see the two curls, two cross products that are the answer. Yeah. It's up to you. I personally like that notation, though. For that problem, certainly. Other homework questions? Yeah.
So for problem 94, if we set x squared plus y squared plus z squared, if we set that equal to t, that we did that.
For problem 94, if you were to rewrite that in terms of spherical coordinates, to start with, it's, what is it? It's k times the vector field, k times vector xyz divided by x squared plus y squared plus z squared to the 3/2, right?
Yeah.
This is actually the Coulomb field. It's the reciprocal. Its magnitude depends on the reciprocal squared distance. This is, in fact, the force field for, like, a point charge or gravity. And so in terms of the spherical coordinates, this is rho cubed down here. So what you're looking at is F equals to, this up here is what? This is k rho hat divided by rho cubed. So in spherical coordinates, this is just straight up k rho hat over rho squared, which you can explicitly see the magnitude is k over rho squared, which is to say that it's the inverse square law. But this is useless unless we actually have the formula for curl and divergence in spherical coordinates, right?
Okay, so
Which is far from intuitive. They're not intuitive. I will tell you this. I'll spoil the answer. This is actually the same stupid question in 3 dimensions that I made problem 1 on the daily quiz yesterday. It's messed up. But if you calculate the divergence of F, you know what you're going to get? For this one, you work it out, you will get a big fat 0. This field diverges from the origin and nowhere else. That's where the point charge is, so to speak. And yet, in some sense, if your naive idea about what divergence is, it does kind of look like it's diverging everywhere, right? The field's always spreading out, but where is it diverging from? It's diverging from the origin. That's why so the divergence is not defined at the origin. It's infinite there. There's a singularity. Yeah.
Wait a minute, where does the row in the numerator come from?
Guess what the curl is here?
Okay.
The curl is also 0 when you work it out. This is a straightforward calculation in terms of the Cartesian coordinates. You can just work it out now. You don't have to wait for me to send the announcement. But it's a trivial calculation if you have the formulas for the curl and divergence in spherical coordinates. It's like a line. Most of you need practice differentiating anyway, so it's a good exercise for you to just try to do it in Cartesians. It's not a bad idea at all. Yeah?
What is the
Oh, well, what is this vector field, x, y, z? The length of it
Oh,
is the square root of x squared plus y squared plus z squared. So in fact, the formula for rho hat in terms of Cartesians is x, y, z divided by the square root of x squared plus y squared plus z squared. But I really just think about it directly as the x, y, z vector is the position vector, which we can write as the distance where we are and then pointing in the same direction from the origin. That's what rho hat means to me geometrically. You go rho out, and you keep going in the rho hat direction. That's what the x, y, z vector is. That's the position vector based at the origin. But here's the algebra. You solve this, right? That's rho. Anyway. Other questions? Shut up. Probably telling me about my minions. I don't even play minions. I got put on there for my kids, you know? But no, I got to claim a reward for my cars game. I got to fix these. I don't play that either. I only play Angry Birds. That's it. You know. Sometimes that Batman Lego game, because they leave it on, it's interesting. But I'm sorry, I keep ruining the answers for you. But yes, you should be able to work out that both the curl and the divergence are 0 in this problem. That's not entirely honest. They're 0 everywhere except for the origin, where this vector field is technically undefined, right? 0, 0, 0, we had trouble. So guys, I'd like to continue talking about this just a little bit more. Special case, right? The special case that I got a little bit confused about last class, and I don't want to make sure, I want to make sure my confusion does not spread to you. So let me just take another 5 minutes to talk about the idea of the deformation theorem once more. So I have in mind the case that we're looking at. You know, we've got two curves, all right? And let's just, for the sake of discussion, say that they're both counterclockwise oriented, C1 and C2, right? Both counterclockwise oriented, right? And I want to focus our attention on the region between them, right? So this R is you know, it's an annulus, right? And the boundary of R is what? Boundary of R by definition is, okay, the outside's good, but the inside I have to disorient to be consistent with the orientation of R. Minus the C1 curve is actually clockwise oriented. That's what I need, technically, to be the positively oriented boundary of the region. That's definition of boundary R, actually. Like I told you, imagine yourself walking along the edge. It should be on your left if you're going in the positively oriented way. So we walk counterclockwise around the outer edge. You look to your left. What do you got? Left, right, if you want. So this is already positively oriented. On the other hand, C1, if you can imagine yourself walking in the direction of C1, the left is, oh no, it's outside the region, right? So he's actually got to walk this way. That's the positively oriented way to walk on that edge, which is why I wrote that the boundary of R is, in fact, C2 union minus C1. All right? These two different forms of Green's theorems mean different things. So suppose, first of all, let's suppose that the curl of P, Q, 0 is equal to 0 on R. Then what happens to this theorem? We get that the integral over the boundary of R of f dot dr, right, is straight up 0. But what is the boundary of R? See, but this is to say that the integral of C2 union minus C1 of, you know, p dx plus q dy is equal to 0, which then implies that the integral over C2 of p dx plus q dy is equal to the integral over C1 of p dx plus q dy. Or if you like the other notation, the integral of f dot dr is equal to the integral of f dot dr for the first curve versus the second curve. This is an example of what I call a deformation theorem. The idea I have is that we take, you can imagine the first curve and you can just kind of imagine expanding it, right? You can kind of just expand the first curve out to the second one. And as you do that process of expansion, right, you're going through an annular region where the curl is 0. What this theorem says is that if you make such an expansion of one curve to a larger curve, and in between those, here, let me write some, here's the actual, so maybe I'm taking the first curve and then I'm thinking about like expanding it out to here. You see what I'm saying? I'm deforming the first curve to the second one in my mind. That's the idea here. If I was to draw it as some sort of vain attempt at an animation, it's like this. Right? And so you're like expanding the first curve to the second curve. In the process of the expansion, you're expanding in a region where the curl of the vector field is 0. If you do that, you're not changing the work done around the loop. This is a deformation theorem, right? So that's one thing we can do with Green's theorem, directly like that, right? But there's another thing here. We could also have the divergence of this vector field PQ0B0, right, on the region. And then what? Then that would give me that the flux through the boundary of R was equal to 0. That's what this second divergence form of Green's theorem would tell me. Because I'm assuming that the area integral is 0, right? So the net flux is 0. What's that mean? So the boundary of R has two pieces, namely the flux through C2 minus the flux through, well, plus the flux through C minus, minus. Anyway, let me get to the point here. This implies then that the flux through C1 is equal to the flux through C2. There's no new field lines stemming from the region between C1 and C2. Does that make sense? I mean, that's what it says. So you're like, okay, well, that's great. I'm glad you're excited about these different forms of Green's theorem. What does it matter to me? Well, there are all kinds of problems which are based on you understanding the concept I just shared with you. Here's one. Consider f of x comma y equal to x minus 1. Let me rewrite it. 1 over the square root, well, excuse me, I'll get it eventually. 1 over x minus 1 squared plus y squared, x minus 1 y. Calculate the integral of f, well, let's calculate flux of f through the curve pictured. So here's 1 comma 0, and the picture I have in mind, the curve I have in mind is this. There you go. Calculate the flux through that curve. So here's how you do such a problem. First of all, you recognize your instructor did not give you a formula for the curve, so there must be some kind of trick here, right? I must not actually be testing you on direct calculation of that. I'm testing you on some concept, in particular, the deformation theorem. So the question then you have to ask yourself is there a simpler curve, right, which I can put inside that wacky curve, where I can actually do the calculation straight up, and it's not bad? I can. If I do a unit circle for example, this unit circle right here, right, this guy, let's call it, C1. So C1 has the formula x is equal to 1 plus cosine t, y is equal to sine t, 0 less than or equal to t less than or equal to 2 pi. We actually worked this out yesterday, right? Yesterday, problem 1, we saw that the divergence of this vector field f is equal to 0. Except where? The origin, but in this case, yeah, 1, 0. 1, 0 is the bad spot. But otherwise, that divergence was 0. And I claimed that the integral around a little circle a little circle that encircled 1, 0 would be 2 pi. But I thought about it. I thought it would be good for us to actually calculate that, since I did calculate it, but I did it in a kind of sneaky way. Let me do it in a less sneaky way. Here's a parameterization of the curve, right? So what is your dx? Minus sine t dt, right? What's your dy? Cosine t dt. And we're trying to calculate the integral along C1 of what we got. We got x minus 1 dx plus y dy divided by x minus 1 squared plus y squared, right? So what's the denominator do on this circle? If you plug, on the circle C1, what's the equation of the circle C1? C1 has actually got the equation x minus 1 squared plus y squared equals 2, 1. So on C1, the denominator is just 1. What's x minus 1? Well, x minus 1 is cosine t, right? dx is minus sine t dt. Now, in fairness to Ripken, I think this might have been what you were trying to calculate. Maybe? I don't know. It's within the realm of possibility you're trying to calculate this. Let me believe you're trying to calculate this. Let's see here, sine t, I'm entitled to my own facts, right? Are we entitled to our own facts or our own truth? I forget. Which one was it?
We're entitled to our own alternative.
We're entitled to our own alternative facts. Ah, a Trump supporter. Let's see here now. Sorry. I know not enough of your life is about Trump yet. Let's bring it here. Let's see here. Cosine t. Is that right? Oh, man. Oh, stink. What have I done? Tell me I made a mistake here.
Yes. Negative sine t dt.
I'm an idiot. What am I calculating here? What did I just calculate? Why is this 0? I mean, it is 0. I mean, what I wrote here is 0. That's not a miscalculation. But why is it irrelevant to the question that I've asked? I did not calculate the flux. What did I just calculate? What is that, what I just wrote there? Work. So my point to you guys is you need to divorce yourself from this confusion, okay? You should all be screaming at me, that's not the flux you're calculating. To calculate the flux, we have to do what? The flux through C1 should be the integral over C1 of what? How's it go? P dy, which is what? Y dy minus x minus 1 dx, right? Minus q dx. I put the denominator downstairs. So that works out to integral from 0 to 2 pi of, well, y dy is y dy, y dy, y dy. Oh, come on. Did I just do it again? Come on. Seriously, look at this. I have a problem. It's y dx. Right, guys? So maybe I should force myself to do something like, I'm sorry, I need to get glasses or better memory. P dy minus q dx. Write that down. P dy minus q dx. All right. The p is x minus 1. Ah! I'm sorry, guys. We will eventually get through this. All right. P is x minus 1 dy minus the q, which is y, dx. All right. Now, what is that? X minus 1 is cosine t. dy is cosine t dt. Minus y, which was sine t, and dx, which is minus sine t dt. And of course, divided by 1. So what do we have? We've got the integral from 0 to 2 pi of dt, also known as 2 pi. Hoi. So, once you chase down your demons about what does it mean to calculate flux explicitly for a vector field, right? Don't calculate the wrong line integral, like I started with. Then you can easily calculate the flux through the unit circle inside there as 2 pi, and then by the deformation theorem, for the divergence form of Green's theorem, we know that the flux through the crazy outside curve is also 2 pi. Because we have also calculated in our previous work that the divergence of this vector field is 0 between those curves. All right? We could also, for what it's worth, calculate the work done by the vector field over the purple curve, right? So this is the work done over C1. The work done by F along C is also what? It's also 0, because we've also calculated that the work done by that vector field over the unit circle is 0. Of course, we could also calculate the potential function like we did yesterday for this vector field if you wanted to. But anyway, enough. We must go on. Any other questions about homework before I do go on? Seriously? What now? My brother is sending me a link to something called Donald Trump versus Talking Heads. I'm intrigued. I'll wait. Sounds like some sort of auto-tuning. Let's see here. So what's up next in this course? In fact, our final big topic is the problem of calculating and understanding flux through surfaces. Not curves, but surfaces. So this is all kind of a two-dimensional warm-up for the main event, which is now. All right, so we want to talk about surface integration. The surface integral. So let me get right to it. Here's the definition for you guys. Given vector field, let's say F, which is continuous, let's say, near surface S. To be more specific, it's an oriented surface. Well, let me go on. Surface S, oriented which is, well, I'll just put parentheses, it's oriented with parameterization. How do we parameterize a surface? We use something like R. Well, I often use a big X here, so I'll use that. Big X vector. This is a mapping from a domain, which is a subset of R2, to S. So we have a parameterization, big X, of the surface. We've got a vector field F, right? How do we define the surface integral? Well, the surface integral, and I debate whether or not you really need two integrals. I mean, I'm not a slave to this. You could put two integrals because it's kind of like a double integral. Opinions vary here. One integral sign will do. I mean, anyway, we're defining. This is no meaning in and of itself. It's just a notation to say, hey, this is a surface integral. F dot ds vector. So this is what we're defining, this object, the surface integral. This is equal to the double integral over the domain of the parameterization of f of the parameterization, all right, dotted with partial x. Oh, I'm sorry, that's not the definition. Un momento. I'm slipping up here. I was about to write for you the formula that we always use to actually calculate it. All right. So, but the definition is more, a little bit less useful, but a little bit more easy to understand geometrically. So what we do is we take f and we dot it with the unit normal. The unit normal to the surface. And, well, I'm not sure I want to. So let me make sure I'm actually lining up with my notes. I have, yeah. Well, I use a little n, so I'll fix that. Little n hat, and then ds, without the vector sign. Now you might wonder, what is that? Where an integral over the surface of like a function, a scalar function ds, is defined to be the integral over the domain of f of the parameterization, like this. And what's the ds? Well, ds is the square root of get it eventually here. Well, how to write that most nicely? Oh yeah, I'm sorry, forget the square root. We should just say the length of partial x, partial u cross partial x, partial v. We could write du dv here if you like. So this is the flux of F through S. The thing I've actually given you two definitions here. This right here is the so-called scalar surface integral of F over S. Here, the little f is not a vector field, it's just a function. So the latter thing I just underlined in green, can you tell me what it would mean? A very important example of this. What would it mean if I, for example, was I just to put the function equal to 1, what would we be integrating there? So if I'm integrating over the surface of 1 times ds, that would be the integral over the domain of the parameterization of the length of partial x, partial u cross partial x, partial v, du dv. What's this a formula for, actually? What do you think it should mean, the integral of 1 ds? big ds. Not the integral of little ds over the curve was arc length, right? What? Yeah, this should be the surface area of S. Before I do anything more, let me show you. And so what is this right here, guys, geometrically? This is what? The component of F in n hat direction. Now, I guess I need to tell you what n hat is, huh? Otherwise, it doesn't really, it's just a formula, right? So here's a picture of what's going on. Let me hazard a picture here. So we've got our parameter domain, u and v, right? Here's the d. The parameterization maps that up to some surface S, right? That's what the x map does. So then over here, we've talked about this before, but you've got x sub v and you've got x sub u, right? Where I'm using the notation x sub v is actually partial x partial v, and x sub u is partial x partial u, right? These are the coordinate velocities. These are the velocity, the velocity vectors along the coordinate curves, the u or v coordinate curves, holding u or v fixed and letting the other one vary. And if we take the cross product of these two, remember what it did for us? It gave us the normal, right? The normal was xu cross xv. Remember? Talked about this a little bit before. So if I'm thinking about a vector field, I've got some vector field and it's got field lines, right? Right? It's got field lines, right? And they're coming through like this, then, maybe I've got another field line that's going like this, right? So this field line almost just is parallel to the surface. That shouldn't really count, right? Because the field line is not cutting through the surface. It's just almost tangent to the surface. It should give me a very small flux. In contrast, these field lines should count because they're more matching up with the normal. So to count the part of them that matches, what we want to do, so here, this is a picture right here of F. And so F dot n hat is the part of the vector field, which is actually right here, right? This piece is F. Length is F dot n hat. What's n hat? So this is the component of F normal to S. So we're adding those up. This is what we're looking at here. Don't get distracted by this evaluation at the parameterization. That's just a technicality. What we're really looking at here, we could summarize this more briefly as the integral over d of F dot n hat ds. We're adding up the components. We're adding up the components of the vector which are in the direction normal to the surface, weighted against the surface area element ds. That's flux. Now, this n hat, what is the formula for it? Well, it's nothing more than 1 over the length of the normal times the normal, right? Did you see that? So if we go back to my definition, we can find a better formula. Because it doesn't give me joy. Does it? I don't know. Here's some standalone formulas, guys. This is the so-called scalar surface area element. This is ds. ds, and that's equal to the length of, xu cross xv du dv. This is the surface area, the scalar surface area element. See what I'm saying? I'm giving a name to this stuff right here. I'm calling this ds without the vector, right? So people also like to talk about the vector area element, right? And so what do you think that is? ds vector, well, that's nothing more than n hat ds. Oh, sorry, circular. The ds is right here. In other words, ds vector is nothing more than what? Here, let me go back to the start. We've got the integral of f dot ds is equal to, over the surface, by definition, the integral over the domain of the parameterization f of the parameterization dotted with what? With n hat. Well, let me put in what the n hat is. What is the n hat? Remember, n hat is xu cross xv, right? Divided by the length of xu cross xv. So what have I done? So what I'm doing right now, guys, is I'm trying to understand a simplification for the definition. Again, the definition is very geometric, wonderful, but so at the moment, I just wrote n hat explicitly. What is n hat? This is n hat, right? Then what's ds? Well, ds, I mean, what does it mean to take the arc length, the surface area integral of f? It means you integrate the function times this stuff. So this stuff, the ds, right, is the length of xu cross xv, and then du dv. Aha! So this is wonderful. We don't actually have to calculate the length of the normal vector. We don't have to calculate the length of xu cross xv because in the formula, in the formula for the surface integral, it cancels out. And in fact, pragmatically speaking, the formula that I will always use if I'm actually calculating straight from a parameterization viewpoint is the following. Here it is. So, nice formula for explicit computation of flux. Here it is. The integral over the surface of f dot ds is equal to, in fact, the integral over the parameter domain D. You take your vector field, you evaluate it at the parameterization, and then you just take the dot product with this. And integrate. And that's how we calculate flux. So I will probably fill, I don't know, the next hour, hour and a half of class with just working through these, one after the other, until I've developed our entire list of standard examples. Right? How do you calculate the flux through a sphere? How do you calculate the flux through a cylinder? How do you calculate the flux through a plane? How do you calculate the flux through a graph? And so forth. So let me do one. Let us start with something that's actually not that easy, but it's a good one. Let's start with the sphere. So I want to set up, what I want to discuss with you guys is how will we set up the flux integral through a sphere? So really the question that, so this is the question. Example 1, flux through sphere. Let's say SR. Oriented outward. So if I were to draw a picture of it, the ds would look like this. So if you look at what I just wrote down, look at the ds without the vector, the scalar surface area element, the vector surface area element. Look at these right here. Do these have anything to do with the vector field that we're finding the flux of? No, they do not. These are just based on the particulars of the shape we're finding the flux through. So we can start with that. We should start by looking at the parameterization of the sphere, and then we can pick on a specific vector field once we're done with that. So the first order of business we have here is to remind ourselves, how do we parameterize a sphere? So I'll remind you, x. And rather than using u and v, I suggest we use phi and theta. Because those are good parameters to parameterize a sphere, right? We freeze rho equal to r, and we let the phi and the theta vary. That gives a parameterization of the sphere. In particular, this one, r cosine theta sine phi, r sine theta sine phi, r cosine phi. So there you go. That's a parameterization of the sphere, which is basically just based on the notion that the sphere is rho equal to r, right? So just plug that into the spherical coordinate formulas and out pops the parameterization of the sphere. Great. Now, what is the surface area element? How do we calculate it? We need to calculate partial derivatives here, right? So like, what's partial x? Partial phi. There's one of them. What's partial x, partial theta? Finally a 0. Right? There's your coordinate velocities in the phi direction and the theta direction. Then we take the cross product of these to get the normal to the surface, right? So the normal, phi theta, is partial x, partial phi, cross partial x, partial theta. Also known as the determinant. You got your x hat, you got your y hat, you got your z hat, you got your r cosine theta, cosine phi, you got your r sine theta, cosine phi, you got your minus r sine phi, you got your minus r sine theta sine phi, you got your r cosine theta sine phi, you got your 0. You should realize that at the end of this, I'm going to make a statement in no uncertain terms that I categorically refuse to work this out for you again. We are going to calculate the surface area element for a sphere once, and then we will forever refer to this calculation. This is an important calculation because we are fond of examples with spheres. However, we are not fond of doing this calculation over and over and over again. Now, you should do it yourself to be safe, because you never know. This is the kind of thing that an evil professor might put on your test or final to actually work this out, right? And it's something you should be able to work out, but I will not deny it. It sucks. So let's see here. So